Okay, in this video I want to talk a little bit about linearization. Now linearization is effectively using a tangent line to find values or to talk more about a function that maybe is harder to work with. In the olden days we used easy tangent lines to approximate values that were hard to find. So what we've got here in red, this is the sine function. Okay, so this is y equals sine of x. What we have in blue here is just y equals x, and you can see that that y equals x is the tangent line to sine of x at x equals 0. Now the point of linearization is basically that for values near 0, you'll notice that the tangent line and the original function are extremely similar to one another. So if I said to you, I want to know what is the sine of, let's say, 0.1. Well, that's not something we know off the top of our head. We know, pi over 3, pi over 6, pi over 2, pi over 4, and those multiples, but we don't know what the sine of 0.1 is. But you look, 0.1 is, right in here. The tangent line and the function sine x are almost the same. So if I plugged 0.1 in here, if x was equal to 0.1, well, that means y is equal to 0.1. So we could estimate, using our tangent line, that the sine of 0.1 is approximately 0.1 because the tangent line's value is 0.1 and the tangent line and the function sine of x are so similar. If you type in the sine of 0.1 to your calculator, you find out that to 3 decimals, 0.1 is is a great estimate. So again, linearization is really just a couple-step process. You find the tangent line, and then you plug in the value that you want in the original function, because lines are easier to deal with than a lot of other functions. Trigonometric curves, logarithmic curves, exponential curves. It's much easier to evaluate a line than any of those other functions. So here's another example with sine. What if we wanted to find the sine of the value of the sine of 1.5? Well, hopefully you realize that that original function I just showed you, that y equals x, that's not going to work for too many values, because after a certain point, that tangent line y equals x is not similar to the function sine x anymore. So we need new tangent lines depending on what value of x we're talking about. So again, the sine of 1.5, we've got to think about the values that we know. Pi over 2, pi over 3, pi over 6, pi over 4. And those are the ones we know. We could make easy tangent lines around one of those spots. Now I'm going to pick pi over 2. And the reason I'm going to pick that is because pi divided by 2 is approximately 1.57. That's awfully close to 1.5. Okay, I'm just going to put this is very close. It's closer than anything else. Pi over 3 is 1.04. Pi over 6 is 0.5 something. So pi over 2 is the one that we know that's the closest to 1.5. So let's make our tangent line. For every tangent line, we need a point. We need a slope. Okay. So the point, we got pi over 2. If I plug pi over 2 into sine, the sine of pi over 2 is 1. The slope, well, for slope I need the derivative. The derivative of sine is cosine. Plug in pi over 2, I get 0. So my tangent line is 0 multiplied by x minus pi over 2 plus 1, which we could really just simplify to be y equals 1. Okay. So again, I picked a spot, and this is the real point of linearization. You pick a spot that's close to what you're looking to get, right? I wanted 1.5, so I picked the value I knew that would be easiest near 1.5. So I'm making a tangent line for the function sine x at pi over 2. So that's my process right here. I had the point. I found the slope with the derivative. Here's my tangent line. And let me drag this in. I made this graph. You can see that, they're actually tangent at pi over 2, but think now 1.5 is, right here. Look how close they are. I didn't find the actual value of sine of 1.5, but look how similar the line is. So if I plugged, there is no x here, so I would just estimate that the, since it's y equals 1, that the sine of 1.5 is approximately 1. And in fact, it is. It's 0.998. So it's really similar. So you find the tangent line, and you use that tangent line to look at the curve. Problems in the book are set up like this. It says find the linearization. Okay, remember, this just means tangent line. Okay. So let's do that for this function here. We need a point. The point, when we know that x is 9, if I plug 9 in, 5 multiplied by 9 squared plus 6 times 9 is 459. The slope, well, I need the derivative, so 10x plus 6. I plug in 9, so the slope is 96. So my linearization, okay, my tangent line, is y equals 96 multiplied by x minus 9 plus 459. Okay. Now what the book says that's a little bit confusing, that's why I wanted to do this, was it says how good is that 1/10 away? Well, 1/10 away for us, 1/10 away from 9 is 9.1. So we're going to evaluate y, the tangent line, at 9.1. We're going to plug 9.1 in. So we got 96 multiplied by 0.1. So 9.6 plus 459 is 468.5. No, 0.6, excuse me. Okay. If you actually plugged 9.1 in to the function, okay, you took this, you said, okay, what's f of 9.1? Did that on your calculator. You get 468.65. So you'll say they're 1/100th apart. Okay. Linearization simply means find the tangent line and use it, and it will help us. Lines are much easier to evaluate than almost any other kind of curve.